All right, so the idea is that what's going on here is that each one of these is a separate mirror about as big as you can make it. So telescopes up to this point are now, of course, the Keck telescope is an example of a mirror telescope that's arranged in a hexagon. And each one of those mirrors is part of a surface. It's a geometric shape. It's a cross between a hyperboloid and a paraboloid, but it because of the way that the electronics works, each one of those segments in Keck keeps a shape and it maintains the shape. But it has to maintain the shape over a very large distance because it works as a single telescope, as a single optical telescope, which means that to a fraction of the wavelength of light, that structure has to that geometric shape constant against gravity, against wind, against other changes. So the idea to go to larger telescopes is to make the telescopes not so much a single surface, but to make them in a way that some people call interferometry, where each one of these is actually an independent telescope, all on the same structure, but in a structure that can be floppy, so the structure doesn't actually have to maintain the position of all of those mirrors to a fraction of a wavelength. That correction is done. Maybe it's better if I change the color. Is that better? So up over here, what we do is we make the correction for the floppiness of the telescope with a bunch of small secondary mirrors. Piece of ELF, those secondary mirrors are only about this big across. So they're small and they can move very fast, and they can, along with correcting the structure floppiness, they can correct what the atmosphere does to the light. And so the light plus the mechanical structure can be corrected in an interferometer in a way or something that's big and bulky and stiff. So it turns out that to build a telescope, if you want to know how much it costs, what you really want to know is how much does this whole structure that moves, how much does it weigh? And the weight then gives the total cost. And so our trick is to decrease the weight by making the mirrors in a very different way, and by making the optical system in a different way, so that it's not stiff. Stiff means heavy, and mirrors are lighter. So the whole thing ends up being about 10 to 20 times less expensive than a conventional optical telescope. That's what ELF is. It's a cross between what people call an interferometer and what people call a telescope. So
yes, we call them interferometric telescopes.
Yes,
that design type.
Yes. One of the designs in the Colossus webpage is called parfait. Parfait is a French word for perfect, actually. Parfait stands for partial filled aperture interferometric telescope. And one example of that is ELF, the ExoLife Finder Telescope, and it's called that because ELF, that when we look at the nearest exoplanet to us, which happens to be coincidentally around the nearest star to the sun, we have the possibility of seeing continents and structure on the surface of the planet. This is big enough to collect enough light. Actually, so Kevin, your first question was, well, how do we get to this? And first thing we get is we need to know how much area we have to be able to collect enough photons.
Exactly.
And then we have to enough in size so that we can, in optical terms, we say we have the resolution. So the bigger an optical system gets, the finer the detail it is. And in our case, we have to be able to separate the light of the exoplanet from the light of the star. And so that's what sets the size of the telescope. And then the number of mirrors, for magic reasons, has to be an odd number, just because of the technology and the algorithms that we use. And then what we do is we make the mirrors as big as we can make them, given the technology that we have for making mirrors. So those essentially define the ELF structure. Though there's one other. we want the structure that carries this. There's a payload on the mechanical structure, The optical support system, the OS, wants to be as light as it can be in order to carry and point roughly all of those mirrors at the right place in the sky. So this structure that you see is a bicycle wheel. A bicycle wheel is an example of something called a which is a Buckminster-Fuller idea that said that if you want to make something that's mechanically very stiff, out of building blocks that involve both tendons and bones in the biological analogy, where tendons are under tensile strength. Tendons are like ropes, they stretch, and bones are under compressional strength. That combination produces the most stiffness for the least mass. And there's a branch of mechanical studies called tensegrity, which that's all about. And in fact, that's what a bicycle wheel is. So the spokes in the bicycle wheel, even though they're pulling, they're under tension. Critical part of making that wheel very, very strong, I mean stiff, for not having very much mass. And that's the idea in the bicycle wheel that supports these optics.
Yeah, I love this analogy indeed. I ride bike every morning to work, and I'm thinking about integrity now. It's really cool. And to summarize what Jeff said, like interferometric telescope, I just wanted to say it. That means telescope means collecting area. So we need large collecting area. Interferometric means large distance between optical elements, primary mirrors here. So to get the high spatial resolution or angular resolution on the sky, that combination makes it this telescope suitable for looking at small planets around bright stars. So this is Earth-like planets around nearby stars where we can collect enough light. And our estimate that to look at Proxima b, which is the nearby exoplanets around nearby star, nearest star, their size of ELF should be about 20 to 25 meters. That's what we need in diameter. And the size of mirrors like 5 meters across. That would give us a possibility to look at Proxima b and also at a bunch, like a dozen of other nearby exoplanets. Yeah, looks good. Yeah, so we computed that requirement for the ELF to be about 20 to 25 meters. And we also computed some models that we can, from light detected from this reflected light detected from planets, as the planets go around the star and rotate around the axis, rotational axis, we can decompose this information into maps of continents and oceans, if they are there, or whatever surface features we have. Of course, if the features are high contrast, that helps. And if even civilizations somewhere in nearby planets exist, then we can even recover some megastructures which these advanced civilizations would build to support their needs for observation. So megastructures, we think, like, for instance, large power plants or large installations to modify climate environment. So this kind of installations we could see.
So let's
so that is basically idea.
Let's maybe do a thought experiment on that. So let's say ELF was on Prox B looking at Earth. What would they, and then also would they be able to see things like the Great Wall of China, or would we have to have like bigger mega structures on our planet for ELF to see that?
Yeah, the big Wall of China is pretty long in principle, but it's quite narrow. So it's only a few meters across in thickness. Yeah, so this I don't think we will see that, but something like Mars Grand Canyon feature we will see definitely. So or really like say Sahara Desert covered by solar panels, we will see
right.
that. So that is the, I mean, it's still pretty far away, and resolution is limited.
Gotcha. All right, so I missed part of that, but basically you were just getting into the algorithm that you created to be able to make images of these planets.
Yeah, in general, like, why do we need ELF? Of course, we are puzzled by the fundamental question: if there is another example of life somewhere in the universe. Even in the solar system, we haven't found yet anything. Even small examples of life, we still hope for that. We look for that. But if we go outside solar system, we have more chances to find it because it's just much more planets there. In solar system, we have 8 planets now. Okay, it could be 9, 10, whatever, but it's only 10. Also of the order of magnitude of 10. If we go out there, we already know thousands of them, and we know there are billions are there. So there is much more chance to find them. We can start from only very close exoplanets because in order to collect enough photons from reflected from the surface of the planet, we need really big telescopes. And we start from ELF. Jeff said it's inexpensive. Maybe he can continue and explain that. And that's the first step, and we have to do it. Jeff, maybe you add some on the cost. If he's there, he got frozen. Everybody got frozen now.
Is he frozen?
I know, you're
so
moving.
Jeff also.
You're moving. Look, you like tardigrade, got frozen and revived.
the cost, and then
Okay.
also too, maybe if you could get into just the metamaterial we're developing and how that differs from like current technology.
Yeah, maybe you can explain why the cost is small.
Well, it's all relative, right? So compared to an optical
relative.
telescope of that size, something that we can't build right now with the resources that exist in astronomy. So the idea, as we said, is to be able to build telescopes with new technology, and we've started that with the Planets Telescope up on the top of Haleakala. Just one example, mirror segments. It's a mirror segment which actually doesn't go quite as far as what we need for this, but it tests some of the optical principles that define how you take light, and you might combine it in a single off-axis optic. So this Kickstarter is aimed at allowing us to take it's about the second step towards making mirrors differently. Right now, mirrors are made by grinding glass in a way that we've done for almost 200 years. The problem and the limitation in that abrasive technique for making mirrors is that what we really want is we want a smooth surface with a mirror. Your window glass is very smooth. When you take a mirror surface and you grind on it with basically fracturing the surface. And so to get to the right shape, you fracture the surface, remove enough glass, and then you go back to smaller and smaller particles to try to recover the smoothness of the mirror. We could do so much better with glass mirrors if we could start with glass, which is fire polished. Its float glass is created by a process that leaves the glass essentially molten as it hardens, and it's not fractured. If we could start with window glass and never abrasively polish them, we don't have to do this sort of one step forward, 2 steps backward that we do with polishing, where we crack the glass, we make a rough surface, and then we go to smaller and smaller particles to make it smoother.
Jeff, real quick, how much smoother is fire polished glass than traditional glass? So like how much smoother is fire polished glass than, like, let's say Keck or something like that?
It's a good question. So you can't actually see the difference by looking at it with your eye, but in an astronomical mirror, typically surface is which we call it micro roughness, and we can see it with a microscope objective and what's called an interferometry measuring trick. That roughness is a roughness on the scale of well, it's many atomic diameters is the roughness, and the reason why that roughness is bad is because it scatters light in all directions. What a mirror does, or a smooth surface, light exactly where we want it in our image. And the diffuse, we call it diffuse scattering. So there's a glow that you'll be able to see off of an abrasively polished pieces of glass from all directions. So if you shine light on it, you'll be able to see that scattered light in abrasively polished mirrors is about 10 times worse than it is in glass that's fire polished. And so we call this is better by not quite 10 times, but the scattered light is worse by about 10 times for conventional polished glass. The other problem with that process is that art form than it is a science. And
right.
We now have, with the technology, with basically the ability to print structure on big pieces of material, in this case, big pieces of glass, we can build mirrors that start out being close to the right shape. And for us, that's a parabola or an off-axis parabola. And then we print structure on the glass in what we call a metamaterial, because it's this sort of, once you make this structure, a printed structure, we call 3D printed structure, and then another reaction surface of glass, it's about this thick. It never comes apart. It is a unique material that now has a electronic structure in it that we use to go from what starts out as a close parabola, not quite optical, and then with the control that's built into it, we can shape it optically parabolic.
And then what would the thickness of this live mirror be, including the polymers, compared to like a Keck with its actuators underneath that?
Right. So the conventional telescope mirrors get their stiffness from a certain amount of glass and steel structure underneath them, and the combination of that steel structure plus the glass makes it stiff. Now, actually, if you go back 40 or 50 years, mirrors were stiff because they were just very thick pieces of glass. So the polymer mirror is, but it's several feet thick, and it gets its stiffness from that thickness of glass. The Keck mirrors are actually the thinnest mirrors around in large telescopes, and they're about at the center of each of the mirrors. And then there's a mechanical structure that adds the additional thickness, the additional stiffness. So it's that combination, that mating of glass, which is thinner than several feet thick, which was polymer, to a steel support structure that gives the Keck mirrors their ability to decrease the mass. That's the progress in the last 50 years. The next step in that progress is about where we go from something that's this thick to something that's this thick. We still have to have a structure in the back of it, but that structure can be lightweight. And now this structure, which is 2 centimeters thick, is this metamaterial. It's this composite of base and what we call electroactive polymers that provide the idea of it's a polymer muscle. Essentially, it's a muscle which creates a force, and for which we can measure forces, and we can the surface of the mirror in a way that allows us to put lots of little tiny muscles in between the two. It's a sandwich of glass.
Yeah,
Awesome.
I want to add here, just for Kickstarter, we actually asked for support to build a prototype of this mirror, metamaterial for mirrors, and that was muscles, electromuscles in between, and we build a piece of this mirror, depending on how much money we collect, big enough to test all the responses we believe this mirror has to have. So that is the idea. All right.
Yeah. So,
Thank you.
Kevin, are you keeping track of questions? I'm not watching.
Yeah, actually, there's just a couple I was going to read off from Ken. First one is, when is the Planets Telescope starting operation? And then he had as well is, how much improvement will this be over current adaptive optics?
Okay, so the Planets Foundation board is composed of basically 3 institutions: the Tohoku University in Japan, the Brazilians have just joined, and the Kiepenheuer Institute in Germany. Hawaii is involved in many ways. So we should say, I guess there are 4. And we're in the midst of modifying a building on the summit of Haleakala for the, we're in the process of getting, so we have permits for that, but they're building in Hawaii is somewhat involved. We hope, if we finish the funding required for the building, we hope to have the telescope operating in a year and a half time. The question about it.
Yeah, 2019 is a realistic time to think about it. Yeah.
The question about adaptive optics is interesting. Adaptive optics and active optics are 2 ideas that exist in current telescopes. Adaptive optics is that if you take a mirror, which currently is typically small, although not always, there's an adaptive optic mirror in the Large Binocular Telescope, which is currently the largest working one, and that's probably about 25-30 centimeters across. And those mirrors are designed to relatively small errors in the optics created by the atmosphere. To do that, they have to work fast. They have to be able to change the shape roughly 1,000 times a second. And the active mirror that we're talking about in each one of these elements of the ELF, that active mirror has a relatively large correction range. So actually, it's a fraction of a millimeter that each one of the actuators in this metamaterial muscle can change shape by. The glass won't change by that much. The potential for fractions of a millimeter. It's slow, so it's there to correct the shape and do it maybe a couple times a second in response to the local environment changes due to tracking and the change of gravity or the change in temperature in the environment. The correction for the atmosphere takes place in little tiny mirrors. So each one of these has its own secondary mirror, which is about this big. And that is the adaptive correction. That does the fast correction 1,000 times a second. And that corrects the atmosphere problems. It's controlled. It might be that we can make these meta material on small scales that are very fast. We're not certain of that. But we could always go to something like the Large Binocular Telescope technology that uses very, very thin pieces of glass and then essentially voice coils, the same thing that works in your loudspeaker design, to push and pull on the glass surface. But that would happen over fast time scales. So the improvement that we're talking about is what we call active, and it's quite active mirrors. Typically, the density of and usually they're big hydraulic or pneumatic actuators that work on the back of a mirror surface. For example, just up the hill from us is the Air Force AOS 3.4 meter telescope. It has about 100 actuators on the back surface. We're talking about a mirror, an active mirror, that because we 3D printed, could have 1,000 or 2,000 actuators. So the density of actuators is an order of magnitude higher, which is what we need to be able to correct our no polish mirror surface. So we want to be able to take your window glass. Window glass is very, very smooth on short distances. On longer distances, the window glass is very wavy. It doesn't make a good. So the structure in the metamaterial corrects the longer scale fluctuations and leaves the short, smooth surface that we need. And it does it by having a high density of these electroactive polymer muscles on the back surface.
Yes, and another improvement you mentioned earlier is that all these mirrors off-axis. So that off-axis design actually means that there is no obstructive structure in front of the mirror, like you see on that our LED model of ELF. All mirrors are exposed to the sky without any structure in front of them, and that allows actually the light then goes to the secondary without any interfering or scattered light construction, and that allows adaptive optics work much more efficiently.
So another thing to notice in the way astronomers have been building telescopes with lots of mirror segments is in the case of Keck, there are 36 mirror segments, and each one of them illuminates a big part of the secondary structure. So it's a very different optical design. And it's required because it's what's called a wide field telescope. So you could ask, how can we get all these advantages with such a telescope, and why aren't all telescopes now built this way? Eventually, we will have other telescopes built this way that do other problems, but the main difference, the telescope looks at a very tiny piece of the sky at once. This is a telescope that we want to use to look at individual stars with exoplanets around them. And so the piece of the sky that we have to see is a very tiny piece of the sky. It's, in astronomers' terms, it's a tiny fraction of, say, the diameter of the moon in the sky. The Keck telescope, large astronomical telescopes, are designed for studying clustering of galaxies, or they require a large field of view because they look at many objects at once. And that means optics are fundamentally different. In our case, each one of these mirrors has its own individual secondary, and no other element shines light onto that secondary. So in that sense, the Colossus or the Parfait are
planets as well.
Are telescopes that are scalable. Each one of these elements is the same, and it wouldn't take too much effort, for example, to convert this of the bicycle wheel structure. We could build this with a few segments and then add more as we go along to increase the amount we get from an exoplanet, or to improve the ability to separate the light of the exoplanet from its star. So it's that scalability, and as Sveta said, the fact that there's nothing obstructing the light. Each one of these is a segment of a big parabola that if you could draw the whole parabola would include all of the mirrors. But in our case, we segments of that parabola to make the ELF.
This is great. Also, there.
Yes.
Explaining that, Nadia has a great question. She is asking. She says, "Hi, will you mainly observe transiting planets?"
No, we will observe all of them because this is the telescope which is will resolve the planet from a star. So we'll use technique called direct imaging in astronomy. So you separate light of a planet from the light of the star. So we'll monitor the light reflected from a planet. And so in this technique, a planet doesn't have to be transiting. So we'll see all of them, transiting and non-transiting.
But let me amplify that a little bit, because that's a really important question. So you know that to observe transiting planets, you can do that with your backyard 8-inch, because you can't actually have the accuracy. Usually it takes more effort. But when a transiting planet is measuring small changes in the brightness of the stars as they pass in front of them. And that's of course a fantastic technique, and Kepler used it to all of our advantages in understanding the exoplanet world. But very few, or fraction of the exoplanets that we could actually see can be seen that way because the probability that things line up so the planet passes in between us and our telescopes and the star behind the exoplanet is relatively small. So this idea means we can see all the exoplanets, assuming that their separation is large enough from the star. It's pretty much independent of the orientation. So that dramatically increases our ability to see more exoplanets. It lets us see the light of the exoplanet and separate it from the light of the star. And that's the key to being able to study life and civilization potentially on those exoplanets. Now, there is interest in having a big telescope that can see a transiting exoplanet, but that's really a secondary concern, because in that case we'll have more sensitivity to see just the light that passes the atmosphere along the edge of the exoplanet. And so we'll learn something from that. But the great advantage of ELF is in direct imaging. That's the thing that can't be done elsewhere. And here's an important way of understanding how significant the size of the telescope is. The ability to see the exoplanet becomes like the fourth power of the diameter of the telescope. So when we go from a current, which is say Keck, to ELF, which is 25, 26 meters across, that improvement, so that's a factor of 2.5 or 3. The improvement in our ability to see exoplanets, factor of 2.5 to the fourth power. It's also the reason why when we go to space, there's no great advantage in this problem, despite what you might think. There are advantages to going to space, but for the direct imaging problem, when we are able to produce a diffraction limited telescope, something in the atmosphere, the expense of going to space with a 25-meter telescope is enormous, and none of the space projects that you've heard about to do exoplanets have the diameter advantage that something built on the Earth that's this large can do. And just
yeah, the cost is enormous. I'm sorry, just pinch in. Yeah, JWST is $10 billion, and we talk here about 50 to maximum 100 millions. So this is a big difference.
Yeah, so the cost differential to put a telescope on the ground compared to putting it in space is at least a factor of 100. So, for example, the telescope, this telescope right here, when we have demonstrated the technology, is a $15 to $20 million telescope. $15 to $20 million. The JWST, when it's launched and is in operation, will be at least a $10 billion telescope. And JWST is 6.5 meters across, which is 23 meters across. JWST will do good things for planet transits and for its influence. One of the advantages of going to space is that things are cold. And so the thermal energy produced by the atmosphere and by the telescope itself, JWST won't have to suffer from. We won't from it if we make the telescope very clean, so it doesn't emit thermal energy. And if we make it big enough and we stay away from thermal emission in the atmosphere with some other tricks, it really has enormous advantages.
This is great. This is awesome. I'm having a good time. We're having lots of good questions. And I also just had a follow-up to that. How are we actually direct imaging, you say, all of the planets? How in a technical sense, how that happens? Well,
so this...
Simply,
yeah. Okay. So why do we make telescopes bigger? We make telescopes bigger so they collect. I mean, it's like, why do you have a bigger bucket to collect rain? You'll collect more water. If the photons in an exoplanet is like the rain, and if you have a bigger telescope, you'll collect more of it. But there's another effect, which has to do with the fact that photons are not just drops of water, but they're waves. And because they're waves, in order to tell the direction that they're coming from, to know that they're coming from the exoplanet, not from the star, we need a large telescope. That's what this is. The reason why these mirrors aren't closer together is because we need to be able to accurately tell the direction of the energy of the exoplanet away from the energy that comes from the star.
Right.
That really is what sets the size of that system. Once we do that, we can make pictures. So we'll be able to make a picture, and you'll be able to see the faint image of an exoplanet next to the bright image of a star. Tricks to do that. This telescope is in some ways like a radio antenna, and a radio antenna is a strange thing in the wave world. It uses, we can actually shape we can put a middle of our image where we don't have the light of the star. So we make an image. Normally there'll be a very bright object in the center of our image, which is the star, and then something very faint next to it. With a telescope like this, which is an interferometric telescope, we can actually put a dark spot. We can force the light of the star so it doesn't appear in a particular part of our image. And so if there is a very faint, it comes shining through that dark spot. I think if you look on our website, we have some pictures that show this. We call it dark spot coronography. And it's another feature of this new idea for how you build a telescope, which says that you create a dynamic way of moving the scattered light around. And it's in many ways, it's not something completely new to radio antennae, but for optical antennae, it's a pretty cool thing that allows us to make an image with a dark spot that helps us see the exoplanet light unobscured by the glare of the bright star. And remember, the star can be 100 million times brighter than the exoplanet. So that means if only 100 millionth of the energy comes from the star and appears in the image where the exoplanet should be, it could be the same brightness as the exoplanet. So we have to be, this is another unusual telescope, that we have to be very, very careful of the scattered light. And that's another reason, as Sveta said, why each one of these mirrors doesn't have any support structure to sit in front of it to scatter light into the wrong place. You know what a conventional telescope looks like. It has a big mirror and a hole in the center, and then a secondary mirror supported above it. And usually it has some, we call them spider or struts, that support the secondary mirror above the primary mirror. It goes back through the hole in the primer to the instruments. Those struts are terrible things for scattering light, and this telescope doesn't have any of that. I know that's a long.
Yeah, there is a question here from Ken, actually. How did you arrive at trim configuration versus also including mirrors in the center in the array? And Jeff just answered that. We just want to get rid of this spider structure. When you look at images of the sky with stars, you see all those spikes, which like make maybe stars looking charming, but these are the defects coming from scattered light on the abstracting structure which support the secondary mirror. And the idea is to get rid of this structure. And how can you get rid of it? You move main mirror to the side. It's the same parabola as Jeff explained, but it's just to the side. And then you don't have that. We will not see the spikes on the stars when we take an image. We will see them round in each of
part of the
mirror.
answer to that question is that we would like to collect more energy. The more mirrors we have, the more energy we have. But there's a penalty for that. The penalty is more mass and more cost. So the sweet spot to cost and mass and resolution is to put the mirrors that we have out on the edge. And if we had more money, we could arrange it so the structure doesn't interfere, so we don't have the struts in the way. But it's a kind of a diminishing return, because we'd much mirrors as big as we can make them. because there's a great advantage to big mirrors, which is another departure from the current world's largest telescopes. Actually, the 30-meter telescope mirrors are smaller than the Keck mirrors. And they did that for technical, could make them less expensively than the Keck mirrors, they think. But it means that the diffraction, the TNT telescope is actually a pretty horrible telescope for doing direct imaging. Correct, it's difficult. That gets easier when we make these as big as we can and we move them far apart to have the resolution. But your question is good. Why didn't we put them in the middle? It's a trade between mass and cost versus the resolution that we get by having the mirrors out of the edges.
So I just want.
Okay, so
I just.
Yeah, no, maybe you. I just want to follow up on this question. Kent asked. He asked he or she. I'm sorry, asked very good questions. Would this technology be complementary to collaboration with the Starshade program? This is also quite a good question.
Yeah. So Starshade is a project that says single ordinary telescope, and it's like go outside and hold your thumb up, right? Hold your thumb up over the sun, and what do you see? Well, if you're at low elevation, what you'll see is a milky aureole due to scattered light in the atmosphere. If you go to the summit of Haleakala, if you hold your thumb up, all you'll see is diffraction. You'll see a bright edge around your thumb that's created by a wave effect. It's created by the light being actually bent or scattered by the edge of your thumb. But you'll see a much darker sky. So the idea of Starshade is that if you make a starshade you can minimize that diffraction effect, and you can use a regular telescope, like your eye is a regular telescope, to see something faint, like an exoplanet around an individual star. Starshades can have enormous sensitivity to very faint objects, but again, they are done in space, and so there's this huge cost associated with that. Now, WFIRST is going to be a good telescope. It's a single dish telescope in space. There's a plan to use starshades, a starshade with WFIRST. But remember, there's another problem with starshades, which is that you can look at one star and then you have to slew your telescope and your starshade around by astronomical almost. So the other thing is that the starshade has to be far enough away that you can get in close to the star with the block light to be able to see the exoplanet. I would say the answer to your question is yes, Starshade is complementary, but we hope to do most of what a starshade can do with a well-designed ELF-like telescope. Starshades will look at individual stars with great sensitivity. So it would be a good plan to build a starshade to look at Proxima b. Right? It's an amazing thing over the last 2 years that the nearest star to the Earth, aside from the sun, has an exoplanet. It's kind of telling us that lots of M dwarfs, maybe all of them, have Earth-like or habitable zone planets around them. So there's going to be an enormous need to look at those exoplanets. Starshade should do the same thing, but because the habitable zone around these very faint stars is so close to the star, the starshades have to be very far away from the telescope we have in space to be able to do this. So the interest in looking at M dwarfs is enormous now, because we've discovered that remember, most of the stars in the galaxy are M dwarfs. Now, some people, for other reasons, the activity of M dwarfs or the tidal locking of the planet, life is less likely. I don't happen to believe that, and we're going to learn that subject by observations with an ELF-like planet. It's going to be hard to do a statistic with starshades just because the habitable zone is in angular units so close, and in physical units so close to the star.
Kevin, you wanted to ask something, you said.
Oh, just a follow-up to what you guys were saying before. I just wanted to kind of say something in different words. So, you know, effectively, there's a star out there, and there's planets orbiting it around it. It may or may not be in our line of sight with ELF, but you're saying through this algorithm that we can detect reflected light off of this star, regardless if it's in our line of sight, and that's all of the planets or a good chunk of the planets around it. And I don't know, to me, that's astonishing that it doesn't even have to be in the line of sight, and off of the reflected light from the sun that then bounces into ELF, you can actually make maps of each one of those planets.
This is how we see planets in the solar system. Planets in the optical light, they don't radiate much. What we see by eyes in the optical light and with the optical telescopes is the light reflected from stellar light or solar light reflected from planets, and that allows us to, and it reflects differently from different features. So on Mars, we see polar caps, which are very reflective, and we see desert, which is not so reflective. We see color structures, and on Jupiter we see all these clouds of different colors, again in different structures, and that just because light scattered differently by different particles and different surfaces. And that's the same idea. We can look at exoplanets in different colors, and then obtain these images in different colors, and then we learn what not only how they look, but also what's the physical condition there, what is the composition of this of the surfaces and the atmospheres.
Sure.
Okay, and there is a question about the wavelength. What is our targeted range of wavelengths? We definitely want to look in the optical because this is where we can search for biosignatures. And definitely in the infrared, where the atmospheric contribution is also important to decipher. In the optical, we can see oxygen and water. In the infrared, in the atmosphere, we can see methane and water also, and carbon dioxide. And on the surfaces, if there are some biosignatures related to photosynthetic organisms, we also look in the optical because they create this particular absorption feature, which is in chlorophyll known as red edge. So it means that light in the near infrared is completely reflected by chlorophyll containing organisms, while the light bluer than in the optical range is almost completely absorbed. And that feature called red edge, we believe exists not only, I mean, we see that actually all photosynthetic molecules have that feature, not only chlorophyll. And we believe that photosynthetic organisms, they through evolution adapt to the light coming from the star, and such edges we will see from other biopigments on other surfaces, and that also will allow us to detect small organisms, photosynthetic. Well, small and big plants are pretty big organisms, photosynthetic.
So I saw Kent asked another question about whether each segment had a coronagraph, and that's a good question, but the answer is slightly complicated but really fascinating, and that is that if you think of this as a single telescope, it has a diffraction pattern, and the diffraction pattern, if it was a complete disk, would be called an Airy pattern. It would have the light of a star at the center, and then you'd see diffraction rings of light of less intensity as you move away from the center image where that bright star is. Those diffraction rings are a killer for us, because if there's an exoplanet on top of a diffraction ring, then it would confuse our ability to see something very faint. But that's another one of the magic features of this telescope, is if we can actually change the diffraction pattern of the telescope without a coronagraph, without any additional optics. The diffraction pattern of the telescope depends on the exact in and out distance. We call it the phase of these mirrors. So if you could imagine that you move the mirrors by some prearranged amount in and out, the light can come in and then produce an image which is a different diffraction pattern. And in fact, that diffraction pattern can have a dark spot pretty much wherever you want to make it. So because this is an interferometer, we can change the phase of each of these mirrors. We don't actually do it at the mirrors, we do it up at the secondaries, which are tiny up here. And by changing those phases, we can make a diffraction pattern that has a hole in it, which is in effect a coronagraph, but it's a coronagraph achieved with the telescope itself, not additional optics. That is a huge, now all of the errors and the phase problems, there are limitations to all of this, experimental limitations, scale with the diffraction pattern. And so where the diffraction pattern has a dark spot, the errors are also small. And so it's really the ideal way to build an optical instrument, to find something which is faint, to have a tunable dark spot that we can move over our field of view by essentially changing the diffraction pattern of this telescope. So we can, again, just to summarize, we can change the position by imperceptible amounts, fractions of a wavelength. And as an ensemble, the diffraction pattern of that new optical system has a dark spot in it where we can move it, we can place it with respect to the central star where we want to look for the exoplanet. So the answer.
Yeah, we can basically, sorry, just quickly, moving this black spot, dark spot, means that we just follow the exoplanet, and means that we don't maintain this dark background for the whole field of view. Again, this is what makes this telescope dedicated to exoplanets and much cheaper. You give up the maintaining the high contrast in the whole field of view, but you just select a small field of view and you follow the exoplanet with that.
So in radio astronomy, that's called a beam profile. We can create an optical beam profile which is synthesized. It's also called synthetic aperture radar, and it goes by other names. But by phasing the elements of the receiver, and the receiver in this system is this collection of mirrors, we can create something which is exquisite for finding something tiny and faint next to something bright.
Wow.
Yeah.
And is that even an option with like I don't know, something like the VLT or EELT as far as making that?
Not at all. Yeah, this is a big difference to those big telescopes which are planned now. They have a single secondary mirror.
Yeah.
They have many segments in the primary area, but in the second is just single one. And then you cannot do such tricks as Jeff discussed. And that's why there's a big difference between ELF and those telescopes, that we can do all those interesting tricks.
Yeah.
At no much cost,
Sure. This is awesome. It's been an hour. It's already 11. Ken has a.
So another question, yeah.
Do you want to read it, and then maybe, I mean, I don't know what you guys have going on today, but maybe do you want to have that be the last question of today?
Yeah, let's do that. How much interferometry advantage would you have with the 3 or more of these scopes around the planet? So he suggests that if we have several ELF around the planet, can we do interferometry? Wow.
Yeah, well, that's a hard.
Yeah, that's probably difficult. I mean, it's not. Yeah, so it's possible theoretically, I would say, but in practice would be hard.
So the problem in combining the light, so it's where the wavelength is tens of meters or more. We can record, and the frequencies are right. So the light fluctuations are 10 to the 14, 10 to the 15 oscillations per second. The radio oscillations are 10 to the 8 times per second. So there's 6 orders of magnitude in the rate at which the wave is fluctuating up and down. So the way the VLBA works is we don't. So when you telescope with the baseline the size of the Earth in the radio, we do the recombination. We combine the signal from each of the telescopes after the fact. We record it, and then we put it together in what's called a correlator. And the correlator figures out essentially the random path length differences between the telescopes to the central, what would be the central site. So we can, after the fact, by recording the signal, reconstruct something that has the coherent size of the full separation between the radio. In the optical, we don't yet have the ability to do that kind of recording of the signal. The other thing that we're doing in this sort of mixed interferometer telescope is we actually have an image that matters to us. So it's not just a single number telescope, each radio telescope. So the possibility of combining these coherently over the scale of the Earth is going to need probably another generation of technology. The ability to record both positional and phase information in the light at 10 to the 6 times or 10 to the 7 times faster than we currently can in the radio system. Now that idea is a good one, and it could be applied optically, but right now it's a technology that's pretty far away from us.
Yeah, that is a challenge for the next generation. So for the next Kickstarter.
Hopefully.
So for this Kickstarter, we focus on this specific, or say unusual optical design, and otherwise we use the current technology, and that's also advantage. We actually employ the current technology in electronics and 3D printing and optical surface development. We also contribute to that technology, but otherwise it's all realistic, and we don't need stretch our technology to unknown levels. So it's all known components here, and that again makes this telescope realistically accessible in terms of money.
Yes, which is important, very important.
Yes.
All right, Jeff, before we go, do you want to show the polykey real quick, just to hold them both up so that everyone can see?
Yeah.
Another thing I was going to say.
Thank you, Kent, for your questions.
Sure, thank you, Kent.
Yeah, the polykey, I mean, we created this LED light, which Jeff used very nicely for demonstration of the telescope, but we also made some creatures which are really cute, and polykey is a worm living very deep in the ocean near thermal vents, which are extremely hot, and they're cute. They're cute, yeah. So they could be such creatures living somewhere in the oceans on distant planets as well.
Yes.
And tardigrade as well, interesting creature. We don't have yet our manufacturer had them, but we don't have that in our hands to demonstrate right now. Maybe next live discussion we can show it. It's also pretty cute. It's the creature which can survive extreme environments. It just dries out. It lives in the water normally, but then it can, in unfavorable conditions, it can dry out, be frozen, can be thrown in space, and then if you put him back into the water, he is alive again. So this is amazing. And these are just some examples of extreme life which we can find somewhere in space, and which exists here on Earth as well. We always learn from life we have here, and it's so diverse and so amazingly adaptable here. That's what makes supports our enthusiasm to search for such creatures in the space on other planets.
When we get the tardigrade and the Voyager cosmic clock in the mail, I'll schedule another Kickstarter live for us. And then one quick thing before we go is we're going to do other Kickstarter lives with some of your colleagues. Svetlana, do you want to?
Yes, we would like to also invite our colleagues working in biology. so that we can explain these peculiar features of these extreme life examples with tardigrade and polychaete. We can discuss in detail how do they do it? How do they survive at 700 degrees Fahrenheit, and how they can be just dried out and then revived. So this is amazing biological adaptation, and we will discuss that with biologists.
Hopefully, like next week, we can schedule something next week.
Yes, we hope for that. So stay tuned. We don't know yet a date, so stay tuned, and we'll send you information.
Perfect.
Sign up, and we'll send you information.
Perfect. All righty. Anything else you guys want to say before we sign off?
No, thanks, everybody.
No, we're good. Yes. Thank you, you two, for great explanations.
Well, Rebecca and other participants of this chat, listening, thank you for your support. Great questions. Come back again, we'll talk more.